Everyone, thank you for joining for this second JFEG webinar. It is my great pleasure to introduce Professor Jacob Mays. Professor Mays is an assistant professor in the School of Civil and Environmental Engineering at Cornell University, and he obtained his bachelor's degree in chemistry and physics from Harvard, a master's degree in energy systems from Wisconsin-Madison, and a PhD in IMS from Northwestern University, which is where I met Jacob. Professor Mays' research focuses on applications of stochastic optimization and statistical learning in energy systems. And today, Professor Mays will talk about markets for zero carbon electricity. Jacob, it is our absolute pleasure to have you give a talk in this JFEG webinar. The floor is yours.
Thank you, Albert, and thank you everyone for showing up. I know it's late on a Friday afternoon for some of you and very early in the morning for others. Since we're early enough, I think I'll take the opportunity to pick on California, since it's probably too early for any of them to be up for this. So as Albert said, I switched the title to Markets for Zero Carbon Power rather than electricity. And what I thought I'd try to do is give a pretty high level talk about three areas that are I think pretty interesting in the evolution of market design, particularly in the context of a transition to zero carbon resources. Some of them have been in the news recently. You're probably aware that there's an energy crisis globally, so there's been a lot of discussion of this. So I thought it would be interesting both from that perspective and then also from the perspective of operations research, how we can address these issues with the tools that we have. So I wanted to start off with some of those headlines. So if you've been tracking this at all, you've probably seen headlines like this coming out of Europe. This one is from a couple prime ministers ago in the UK, but it says Boris Johnson hints at major reforms to frankly ludicrous energy market. So we have heads of state weighing in on details of market design, which is always an interesting situation to be in from the standpoint of the system operator or the market operator. A few months ago, it was back in June actually, in Australia, things got so bad in terms of the market operations there that they had to make the decision to actually suspend the operation of the market for 10 days. So a lot of turmoil led to that, and that's led to some ongoing discussions in Australia about market reforms there. Just today, or actually yesterday, the Public Utilities Commission of Texas met to discuss some pretty major reforms in the market there. So it's not just Europe, it's not just Australia, it's really a global phenomenon where people are kind of re-examining market design in the context of both the current crisis and then the broader trend toward decarbonized systems. So in that context, this is a headline from far before the current crisis. There was recognition that wind and solar and the growth of wind and solar are at the very least putting pressure on current market design. So I don't think I quite agree that they blow up power markets as this headline suggests, but at the very least, the fact of how different these resources are from the traditional thermal resources we've used to run power systems has caused a lot of stress on market designs. So this has motivated a sort of return to first principles in a lot of ways, and to re-examine what is it we're actually trying to get out of competitive markets. Why do we organize competitive markets for power in the first place? And if you go back to the principle, the idea here is that if we're able to submit to form transparent and complete spot prices in electricity, then that should motivate market participants to invest efficiently, meaning build the right types of resources that we need to run the system reliably and at low cost, and then also operate those in real time. And the theory behind competitive markets doesn't really change due to variability or due to zero marginal cost. So one of the big questions has been, we think we need to change things with all this wind and solar, but if you go look back at the original theory, it doesn't seem to change things. So what's really going on? So I mentioned a return to first principles, and the classics are from the 1980s. Here on the left is Markets for Power by Joskow and Schmalensee, which is the kind of economics angle. On the right here is Spot Pricing of Electricity by Schweppe et al., which is the electrical engineering angle. And the reason I mentioned this is that in returning to first principles, this is really a matter of not just OR, but also economics, engineering, electrical engineering, law, sociology, policy. This is a really interesting mix of disciplines that need to be brought to bear on the design of power markets. But I think there's a particularly good role for operations research, which is I think most of this audience. So I think I'd like to talk about three big OR challenges. The first is around the incorporation of uncertainty and the need for flexibility in the formation of short-term prices. The second is around risk and ambiguity and decision-making under uncertainty and long-term contracting. So this is the long-term investment decisions that get made. And then the third thing, the third topic that I'll mention is coordinating investment in generation and in transmission. So to start off with, it's been recognized for a long time that if you add a bunch of wind and solar to the system, that increases your need for flexibility. So this is one of the most famous charts in power over the last decade, called the duck chart. Where they started to notice over a decade ago that if you add a bunch of solar to the system, it will reduce your demand or your at least perceived demand in the middle of the day when solar is producing. But you introduce first off, you don't really do anything about the evening. So solar doesn't really help your production at this time of day. And then you also introduce this big ramp. So all of the complementary resources need to ramp very quickly from the early afternoon into the evening. So this has been noticed for a long time that the more wind and solar you have on the system, the more demand there is for flexibility from the complementary resources. And so from a market design question, the question becomes, all right, how do we get enough flexibility on the system? So I stole this meme from Brian Bartholomew, who does a bunch of great graphics related to storage operations and markets. And so from the engineering standpoint, we think about this as integrating renewables. But from the market standpoint, how we get flexible resources into the system is by forming prices that introduce a lot of volatility that flexible resources are able to take advantage of. And so the market design question is are we in the short-term price formation mechanisms we're using producing enough volatility to make that a good bet for investors? So ideally, what we want in a market setting is we want the market-based operations leading storage to charge at the times of excess and then discharge later. So another chart from Brian, in the ideal case, we have all this solar generation in the middle of the day. The prices collapse. So this blue line is the price in California. And so what that means is we want the storage to be charging it here. And then the solar comes offline. The price jumps back up to up here in this chart. It's in the $40 to $50 range, and this is when storage ought to be discharging. So this is how it ought to work in kind of an ideal case. So if you were watching California last month or a couple months ago now, this is September 6th, they ran into a situation on Tuesday, September 6th, with extreme hot temperatures. And so they called a statewide flex alert, which basically is a call for conservation They're worried about the grid getting into trouble. And so they were telling everybody, especially between the hours of 4 to 9 p.m., try to manage your consumption. So interestingly, when we look at this, the performance of the system on that day, so this screenshot is taken from 5 o'clock on that day. And what we start to notice is that batteries, this color here, start discharging at around 1 p.m. So what we want to have is we want to be conserving energy until that flex alert is active. So until that 4 to 9 evening period. But what's actually happening is batteries are starting to discharge way before the critical hours. And if they start at 12 or 1 and they're a 4-hour battery, they're basically completely discharged by the time they get to the critical hours. So that's a big problem from an operational standpoint. And if you dig into the reason why that's happening, the issue is that the price is above is running into a cap in the market. And so from the storage operator's standpoint, if the price is already at the cap at 1 p.m., they have no incentive to hold on to it further and wait until the early evening. So the ideal market would say you need the prices to even be higher in the early evening so that storage has an incentive to hold on to it. But that is not being allowed to happen in the California system at present. And it got them into trouble. So they actually did declare the highest level of alert here later in the afternoon on the 6th. So the point I want to make here is that if you get the pricing wrong, it actually can become a reliability problem. Here we fast forward 1 day, so September 7th, same thing is happening, same heat wave, September 7th, 4 to 9 p.m. They issue a flex alert, and people quickly noticed that on the 7th, all the battery operations appear to be better. So we've stopped that early discharge that was starting to occur in the 12 to 1 p.m. range. So the CAISO operators learned quickly and basically are using out-of-market exceptional dispatch instructions to tell all the batteries to sit back and wait. So the issue here is that they're completely not relying on the markets and not relying on the decision support tools that are being provided to them by all the optimization software. They're just using their own judgment and saying, okay, we know this happened yesterday and it didn't work, so let's just manually override and do better. And given the alternatives, this is actually a better strategy to manually override. But as somebody who works on optimization models, you have to think, all right, well, clearly the decision support tools and the market designs that we're providing are leaving something to be desired, because they're having to do this exceptional dispatch in the emergency case. So to kind of sum up the first challenge on short-term price formation, there's this. I've just chosen one example, but wholesale markets for electricity suppress volatility of energy prices in various ways, and the growth of wind and solar kind of exacerbates the flaws in short-term price formation. In particular, some of the current efforts around fast start pricing and ELMP, for those of you who have really been following this, suppress volatility, and that can lead to problems in the long term. And then, if you don't produce full strength prices, then that can lead to reliability issues and out of market interventions, which have their own challenges. So I think there's a big role for OR in both in designing the decision support tools themselves, in terms of when should we dispatch particular, especially storage, but then also in the pricing mechanisms that will support those efficient reliability and market outcomes. Okay, so second big challenge is around risk, ambiguity, and long-term contracting. So I'm resorting to the patron saint of fat tails and risk here, Nassim Taleb, who says electricity is possibly the most volatile commodity out there. And so we've seen a bunch of headlines recently with in Britain a bunch of suppliers in the retail market going bankrupt. In Germany, some suppliers going bankrupt because of their inability to get gas. And this is kind of the genesis of the massive reforms that are being contemplated in a lot of the European markets. The extreme underlying volatility and the apparent lack of ability for market participants to manage that volatility on their own. And the issue, or one of the issues, is that if the dislocations financially are significant, are this significant, then it actually becomes a problem for the idea of having markets at all. So a lot of the movements in Europe are to say, let's move away from relying on competitive markets and maybe go back to something more closer to the traditional vertical integration. The other issue with volatility is that if the financial volatility and the political risk is so extreme, then it can lead to underinvestment. So this is a headline from Texas last year, where the resources on the system were massively less than what they needed to be for that for Winter Storm Uri. And I think part of the story here is that it's quite risky to rely on private market actors to make the investments required for very rare events. And if you don't have mechanisms to financially make that a good bet for them, then it can lead to underinvestment and put the system in a riskier position. So this is a chart taken from ERCOT prior to that event last winter. And the main point here is that in the median year for a power plant in ERCOT, they're going to earn way less than what is required on average to sustain themselves. So they're really relying on rare instances where they have what might be considered windfall profits. And I say they might be considered because it looks like that from the outside looking in, but really what's happening is they need that to make up for the fact that they're losing money most of the time. So they have this really skewed profile of investment, of returns. And so something needs to be done to smooth that out in order to make financing projects, generation projects, viable in markets like this. So broadly speaking, there's two kind of ways for policymakers, market operators, regulators to help do that, to help manage the financial risk associated with investing in these markets and make sure that they have enough resources coming onto the system. The first is to suppress the volatility in spot prices. So this is kind of related to what we were talking about in the first section. If you just suppress the volatility in spot prices, then you can put in caps and things like that, price caps, and that reduces the volatility associated with investing. And then the second is you can mandate contracts. So you can mandate long-term contracts or hedges of various sorts to try to encourage more investment and make investing a little bit more of a secure enterprise, and then also potentially, depending on how you structure them, provide some price protection for consumers. So if you're a regulator, you might be interested in protecting consumers from the volatility in the spot prices, and you might be interested in mandating contracts to help with that. So broadly speaking, my opinion is you want to avoid the suppressing the volatility in the spot prices. This is for kind of the reasons that I was talking about in the previous challenge, where that can really lead to poor incentives for operation and unforeseen consequences. But we ought to be pursuing different ways of mandating contracts and thinking about the best way to do that. So I mentioned this earlier, but wholesale markets suppress volatility and spot prices a bunch of different ways with mispriced intertemporal constraints, operator load biasing, some of the uplift and enhanced pricing mechanisms. There's a lot of new ancillary service products that are being discussed. I'm not going to go into detail on all of these, but there's literatures basically on all of these and the effect that it has on price formation in real-time markets. But the upshot is that it's actually pretty difficult, even in a strictly mathematical sense, to form what you might consider theoretically ideal prices in real-time electricity markets. But as I said, we'd still like to be able to do that in order to make sure we're getting efficient investment in operation. So one of the big challenges is how do we get something close to transparent and complete price signals. It's been recognized basically since the introduction of competitive markets that if you cap prices too much, so if you set spot prices that are too low on average relative to the theoretical ideal, then there's going to be insufficient capacity. So people aren't going to have the incentive to build. And so most systems have kind of recognized this and tried to figure out ways to supplement energy revenues with additional payments. Similarly, but less recognized, if you suppress the volatility in prices, that can also have long-run consequences, where if you have too low volatility, you might get insufficient flexibility in the system. And so increasingly, it's being recognized that if you suppress volatility, it weakens the incentive for flexibility. It weakens the incentive for assets with uncorrelated failures. And so we're still kind of understanding what are the consequences of the various suppression of volatility that goes on in electricity markets. So as I said, I prefer to avoid that. I prefer to avoid suppressing volatility and suppressing prices, and instead think that we ought to mandate some form of contracting. But then that opens up a whole bunch of design choices and how you do that in terms of do you have the spot prices themselves that you can organize the contracts around? Who should do that? Is it a state? Is it a market operator? Is it some combination? Should it be a centralized market or a bilateral market? What contractual form should be chosen? Do we want financial contracts or physical contracts? I'm not going to talk about really any of those decisions, except to say that in order to understand some of those, you can use equilibrium modeling and try to help decision makers understand these various design choices and saying, what are the consequences in terms of the cost, the reliability, the emissions that we'll get out of the electricity system based on the different design choices that we make. And so operations researchers and modelers in general can help inform those decisions with what I've used is kind of equilibrium models, but there's various ways to help those discussions. So just recapping this second challenge, generation resources need some sort of long-term certainty to support financing, and the growth in wind and solar might even exacerbate that by increasing the revenue volatility that the resources will see. The existing mechanisms don't seem to be working all that well, and so there's a lot of room for ideas about reform, and then a lot of room in OR for examining those different potential policy mechanisms and contracting regimes, and analyzing the consequences of their adoption. So the last high-level challenge I wanted to at least briefly mention is coordinating generation and transmission. This is a chart of the interconnection queues in the United States, and I bring this up to mention that the decarbonization goals aren't really just aspirational. this is a chart of what's likely to be built or what could be built in the next 5 to 10 years. And the thing to notice is that it's just utterly dominated by solar and wind, and then storage. So solar, storage, wind are completely dominating the interconnection queues in the United States. So it's realistically the direction that most systems are going. This is a map of the wind resources in the US, and this will be familiar to anybody who is from Kansas, like I am, or the surrounding areas. But it's very windy in the middle of the country, so we have excellent wind resources here. Not so good in the Southeast in particular, or in the western part of the country, even though there are little pockets where you can put in wind farms there. But the moral of the story here is that we need more transmission to get the excellent wind resources in the middle of the country to the load centers, which are typically far away from those. Same story with solar, where we have excellent solar resource. Really, the solar resource is pretty good throughout the US, but in the Southwest in particular. And so the more you're reliant on variable resources, the more you benefit from having the ability to trade across large regions and balance some of the wind and solar output and the demand to the extent that they're uncorrelated. And what we've observed in the US with the growth of wind and solar is that we're not really building transmission at the same pace. So we end up with, in this chart, is showing lots of negative prices, which indicates that there's wind being constrained in the panhandle of Oklahoma and western Kansas and up here in Texas. It's actually a very frequent occurrence to have wind being curtailed because of insufficient transmission to get it out. This is actually back from 2017. We've had a lot of growth in wind and solar since then. So there's quite a bit of need for more transmission. So the couple issues here is that, first off, planning transmission is a very tough problem. These are really long-lived assets. They might last a century. They have long lead times for construction, significant uncertainty, macroeconomic uncertainty, and then they also have significant economies of scale. So we have big uncertainty, and non-convexity is also important. So it's challenging just from a straightforward social optimization standpoint, not to mention the physics. So the circuit, the flow laws are typically just omitted from the high level planning models, just because it's impossible to incorporate everything. So developing a plan, even the best cases, is pretty tough, but making it even more difficult is the fact that there's no single agent in charge of any of this. So we have a whole bunch of different planning entities at the local level that are responsible for transmission. So this is a map of the balancing authority areas in the US. And then we also have the complication that we have private investors, for the most part, building generation, and we have the centralized system planner doing the transmission plan. So we have big agency planning problems and sequential plannings or coordination issues between neighboring regions and between the generation investment and the transmission investment. So we're running short on time, so I'm not going to talk more about that. But the upshot there is that there's, I think, a significant role for OR in both in the planning models, and then also in the process design of how we sequence and how we coordinate, and then also in the cost allocation of who pays for transmission infrastructure when we make the decision to expand it. Okay, so I know we're short on time, so I'm going to close there and say 3 high-level topics: the short-term price formation, the long-term contracting, and the coordinating generation transmission. And I'll leave it there. Thanks.
Perfect. Thank you for the great talk, Jacob. We're a bit short on time, but let's see if we have one question or a couple of questions. Okay, it doesn't seem like we have any questions from the audience. Maybe I'll ask you. Oh, Rayway, please.
Oh, yeah, thanks. I will take this chance to ask my own question. Like for the third part, like coordinating transmission and generation, do you see a possible market type of solution to this long-term transmission planning problem?
No, and I think people have been really trying hard for the last 20 years. At the same time that we introduced competition and generation, people thought, oh, it'd be really nice if we could essentially self-fund transmission expansion through the congestion rents that you get on transmission lines. And I think the basic issue is that the congestion rents, because of the non-convexities, the economies of scale, the congestion rents in an efficient system won't come very close at all to covering the full cost of the line. So there might be some occasions where you could do merchant investment, but it would really be a small part of the overall the investment picture. So I think you do need to have some centralized coordination and cost allocation to really solve the issue.
Jacob, there's one more question in the Q&A. So the question is, how much of suppressing spot prices do you think is driven by politics?
Yeah, a lot of it. And I think one of the issues in modeling it is you don't, it's tough to, encode that logic in a modeling study where, from an optimization standpoint, you just say, okay, we get the dual variables and we say those are the prices, but that's not how it works. And so there's all of these complications. And so I guess the way I see it is that we want to understand the consequences of that model the effect of what goes on when you suppress those prices, but yeah, there's only so much you can do in thinking you can control it, or thinking you can really accurately reflect the way the prices get suppressed.
Thank you so much. So in the interest of time, and we're a bit after 11 a.m., let's thank our speakers again. Thank you for giving great talks for this second JFEG seminar, and we look forward to the next seminar.